Okay, folks, well, it's already 3 minutes past, so we should probably go ahead and get started. I have a few logistical updates that we should discuss. I want to flash homework 8 in front of you, some simple problems on scattering theory, which we began to introduce on Wednesday of last week. We will continue this week and probably all of next week. I am so behind on grading at this point that I am calling in backup. I'm asking a colleague of mine to help me catch up on some of the back grading so that I can get this stuff returned to you in a reasonable amount of time. So working on that. The next couple of weeks, I'm thinking about the calendar and I'm losing my mind because starting a week, 2 weeks from today, basically, I have this week, and then next week is when things start to get underway. We have back-to-back meetings for the APS April meeting, which is big in nuclear physics, and then right before that is the topical group on hadron physics meeting, both of which I am chairing sessions for, both of which I am presenting talks at, so I'm losing my damn mind. So with this in mind, and considering the fact that we are already behind a bit compared to the schedule that we have discussed after the first midterm, and considering the fact that I think everyone can benefit from some time to catch up on assignments, I am thinking that this week we can get through most of the material on scattering theory. If instead of rushing, we take our time with it, then we can probably occupy all of next week too, wrapping up two-body scattering. If we have extra time, say next Wednesday, then I don't think anyone's going to complain if we take some time in class and just do review, practice problems, questions on homework, whatever you guys have. We can treat it like a recitation if we end up with extra time. So for my own sanity, I really do not want to try and arrange to have the midterm next week. That's just not going to happen. So the best that I can plan on is to expect to try and do the midterm the week after that, the week starting the 19th. So if all goes according to plan, then I will be through this insanity by that point and have a nicely prepared sample exam for that Monday, exam for that Wednesday, regrade for that Friday. And we'll do it the same way that we did for the first midterm. This is what's going to determine cutoff dates on when homeworks need to be submitted. So homework 8, which I will go through in a minute, I posted at the end of last week. This is just like 2 conceptual questions and 2 direct calculations on cross sections and scattering. There's no like big concept applications. I do not anticipate assigning any further homeworks between now and the midterm. I think you have enough on your plate, and it would be good to practice more scattering theory stuff, but I think we can do that in class. I don't see any benefit to assigning another homework assignment on this stuff. So this is sort of what the next few weeks looks like to me. Do you guys have any questions or concerns before we review what's on homework 8?
I saw that homework number 8 is due the same day as homework number 7. Is that true?
Yes, that's correct. So homework number 7, I should have posted 2 Fridays ago, but I was late on that. So instead of, I posted it early last week. So instead of making it due last Friday, I made it due this Friday. And I assigned homework 8, the usual end of last week, which would normally have been due this week. To try and balance it out, I made homework 8 shorter. But again, there's no penalties for late submission. So basically, you have until I have to cut off all homeworks to post the solutions for people to study for the midterms. So my apologies for the timeline on that. If I had been more on top of things, then I would have given homework 7 a little bit earlier. And that would have been due last week, and homework 8 would have still been due this week. Is that clear?
Yeah, thank you.
Any concerns with that?
Well, I hadn't looked at homework number 8, but if you say that it's not too long, then it's fine.
Yeah, we'll go over it now, and then you can let me know if you have any questions or concerns. Okay, I apologize. Several people sent me emails over the weekend, and then between Easter and everything else, I'm behind. So if I didn't get back to you, my sincere apologies, and we'll catch up hopefully today. Okay, any other logistical things before we discuss homework 8? Okay, if not, let me share screen for a second and we'll talk about what's on homework 8. Okay, so last week we finished up the photoelectric effect and we began with the introduction to scattering theory. We'll do more of that today. So as Antonio pointed out, this one is nominally due this Friday. I assigned it at the end of last week. But no one's going to get penalized if it doesn't get turned in here as long as you have it in before I have to put a hard cutoff before the midterm. So it's just one page. It's 2 conceptual questions. So altogether, it's worth 15 points. 2 conceptual questions, 2.5 points each. The first one is about cross sections and measurements in scattering rates. We talked about what a cross section is, why you would make it up, and how you use it to compare different measurements. So the first one is you have 2 different measurements. One uses a beam of 2.5 times 10 to the 34 particles per square meter per second and makes a measurement of 3 times 10 to the 4 counts per second. You have a separate measurement which has a lower beam flux but measures a lower rate. So the question is, are these measurements consistent or inconsistent? And that's really just conceptually about what is a cross section and how do you use it to compare different measurements. This one is really about sort of conceptually what the conclusions about the photoelectric effect were. We talked about the final distribution of particles that gets produced. We talked about limits when the energy is comparable to the ground state energy of hydrogen. So if your ground state energy of hydrogen is 13.6 electron volts, this photons of energy, h bar omega of 20 electron volts is pretty comparable to that. So in that region where you are not kicking the electron out with bazillions of electron volts worth of energy, what direction do they go? That's really the main question. We drew some figures about which direction the electrons get kicked out in. So if the beam is moving along the z-axis, the magnetic field is moving along the x-axis, which direction do the electrons come out primarily? Just a simple conceptual question about the photoelectric. Okay, and then the last 2 questions here are direct applications that will be the bread and butter of scattering theory, which is calculate a cross-section. Given a potential, calculate the cross-section. And as we discussed last time, the core of that is essentially you take the potential and you Fourier transform. So you'll notice, for instance, this was the Gaussian potential. This is very similar to the Gaussian pulse that we did in time-dependent perturbation theory. Fourier transform of this looked an awful lot like that. So you will repeat the same exercise, you will Fourier transform the Gaussian, you will multiply it by some factors, and you will square it. And that should give you this cross-section. Nothing too special there. This one is directly out of the textbook. My suggestion to you is that this Gaussian integral is easier to do in Cartesian coordinates rather than trying to do it in spherical. So that's this one. And then part D is another direct application. So this one is the 1 over r squared potential. If part C was one that I took from the textbook, part D is one that I took from the comprehensive exam. Normally, I would put a link to it here, but the physics department just switched its website. And so links that used to work before don't necessarily work right now, and that's in flux. So if you have access to the 2018 comprehensive exam, I promise it's problem number 5. Otherwise, you have to just trust me. The exercise is the same thing. You need to Fourier transform the 1 over r squared potential. But I put some comments down here because that Fourier transform of 1 over r squared is a little bit awkward. You have a singularity when r goes to 0, and that singularity does not integrate cleanly. So you can regulate that infinity a few different ways. They should all give you ultimately the same answer, but the one that I recommend is that you regulate this 1 over r squared by replacing it as 1 over r squared plus epsilon squared. And at the end of the day, you take epsilon to 0. This is a sort of nice symmetric regulator. And if you do this, then you can do the Fourier transform by contour integration with residues. So then you'll immediately be able to pick up poles, for instance, at plus or minus I epsilon. That's the idea. So we will discuss something similar to this in class, hopefully today when we do Green's functions. Okay, so this is what's on homework 8. 2 conceptual questions about what is a cross-section and what is the physics of the photoelectric effect. Direct calculation with the Fourier transform of a Gaussian that you've already done before to get the cross-section, and then a little bit more complicated Fourier transform of 1 over r squared that you need to think about, but that is anchored to the comprehensive exam. Any questions or concerns on homework 8? I anticipate this being the last homework before the midterm. Okay. I think that's it from me in terms of logistics and housekeeping stuff. Any other questions before we dive in with scattering theory, a fresh start today? Okay. So last time we wrapped up the photoelectric effect and we used that as a springboard to start discussing concepts in scattering theory. We talked about what a cross-section is, and we discussed how to calculate things like a scattering amplitude or a cross-section by using Fermi's golden rule. I was really rushing at the end of class and I fumbled some of the factors of 2 pi h bar because I forgot to square things. We will revisit that today, but before we sort of go from that angle, I wanted to take a step back and connect scattering theory in 3 dimensions to scattering theory in 1 dimension that we did last semester in Physics 554. So I will start from a fresh angle today, and then we will come back and revisit that Fermi's golden rule version that we did last time. Okay. So last semester in Physics 554, we did scattering in 1 dimension. And scattering in 1 dimension was very simple because there were only so many directions things could go. So we had something like, given a potential V of x, something like a step potential. The whole idea was that you set up, if you have a wave which is incoming, a plane wave solution, psi incoming, then you solve this as a boundary value problem in the time-independent Schrodinger equation. So this is done as a boundary value problem. So you specify the incoming wave function psi incoming, and this was something like a e to the I kx. And we excluded a wave function e to the minus I kx. So these are the 2 independent solutions in the free particle region, right? So if I've got v equals 0 here and something else over there, I've got 2 possible solutions, e to the I kx, e to the minus I kx, and I choose my initial condition, or I choose my boundary condition to have an incoming wave from the left, which is this term, and I choose it to have no incoming wave from the right, so that coefficient is 0. So given that incoming wave, the question was, what are the possible outgoing waves? And there were only 2 possible things that you could have happen. You could have a reflected wave, psi r for reflected, or you could have a transmitted wave, psi t for transmitted. So the way the boundary value problem was set up is that you specify what particle is incoming, and you ask what are the possible outgoing particles. Outgoing wave solutions. And there were only 2 possible cases. There was the case of reflection, where you had psi r is, let's say, b e to the minus I kx, so something that is reflected and going back in the opposite direction to the wave that came in with the same wave number. Remember that this wave number k is related to the energy. H bar squared k squared over 2m is the energy of a free particle. So this k tells you the energy. For the transmission, we had a transmitted wave psi t, and this had some other coefficient c. It was e to the I kx, but it could have had a different energy. So in this illustrated example of a step potential, it came in with v equals 0. The potential goes out with some different value, so your outgoing particle could have less kinetic energy. And that reduction in the energy from k to k prime shows up here in a different wave number in the phase factor. So this was scattering in 1 dimension. The way that we describe scattering in 1 dimension, the probabilities associated with it, was with reflection and transmission coefficients. And those were related to the incoming and outgoing probability currents. So we will come back and use this again shortly. Let me remind you what a probability current is. The probability current is defined as minus IH bar over 2m psi star gradient of psi minus psi gradient of psi star. Note this might help us a little bit in our calculations today that this is an object minus its complex conjugate. Minus complex conjugate. So anything that's real in this expression gets canceled out. Anything that's imaginary gets doubled. We subtract the complex conjugate. Okay, so for plane waves of this form in one dimension, this current was easy to calculate. So our incoming current was minus IH bar over 2m. Incoming wave psi star was A star e to the minus I kx times the gradient, which in this case is just a derivative. So that is A times IK e to the IKX minus the complex conjugate. So when I multiply this thing out, I get A squared, phase factor cancels the phase factor, and I've got something which is purely imaginary. When I subtract its complex conjugate, I double it. Complex conjugate of this is minus IK. IK minus negative IK is 2IK. So we ended up with minus IH bar over 2m, the magnitude of the wave, the coefficient A squared, and then we had 2IK coming from that difference. And it is not an accident that the minus I cancels the I and the 2 cancels the 2. And we get something which is very physical. Let me leave this picture up here. So what we find is that the incoming probability density is that magnitude of the wave squared, the intensity of the wave, if you like, times h bar k over m. This object here is just the momentum incoming divided by m, which is just the velocity. So what is a probability current of a plane wave? A plane wave is traveling with definite momentum, which means traveling with definite velocity. So this is a total probability a squared, which is moving at a velocity v equal to h bar k over m. So in the same way, we immediately found the probability currents associated with the reflected wave and the transmitted wave. So J reflected was b squared h bar k over m, same k, because this one's coming in from the left, this one is bouncing out also to the left. So they're in the same region of the potential. If the potential is 0 here and this one has wave number k, this one also has the same wave number k. The transmitted wave could be different. J transmitted is c squared h bar k prime over f, or k prime can be different because you might take away some of that kinetic energy in going over the barrier. So once we had these things, we were able to calculate the reflection and transmission coefficients. These things are defined simply in terms of the ratio of probability currents. Probability current out divided by probability current in. So that reflection coefficient was absolute value probability current out for the reflected wave divided by probability current in. And if I take these expressions and I divide them, they have the same velocity, h bar k over m. So those just cancel. And we got b squared over a squared. Similarly, the transmission coefficient is this divided by the incoming probability. This is J transmitted over J incoming. So this was C over A squared, but the velocities can be different because the potential could have been different on either side of the step. So there's a ratio of the velocities, K prime over K. So you have two effects. One is how much of the incoming probability came back, how much of the incoming probability went forward, and is the probability moving at the same speed or did it slow down? In one dimension, this was everything that could happen because in one dimension, there are only two directions. There is that way and that way. So you can quantify all possible final states just by telling me how much was transmitted and how much was reflected. In 3 dimensions, we're going to do the same thing, but you have many directions in which things can go. So we will set up the scattering problem similarly in 3 dimensions. This is an equivalent way to think about it. And it will be essentially a boundary value problem again of the same kind. We will specify an incoming wave in a particular direction with a particular probability current that's coming in. And we will ask, what are the allowed outgoing waves in any angle? And now we have an infinite number of directions it could go. And then we will find the probability current, which is scattered by the potential. And that will describe not a reflection and transmission coefficient, but a scattering cross-section that tells you the probability to go in a specific direction per unit incoming current. Okay, so the only other comment that I want to make about this is the general setup of how you evaluate reflection and transmission coefficients. The way you actually do it in practice is you have to plug it into the Schrodinger equation. You have to actually solve the boundary value problem for a given potential V of x. That boundary condition is what's going to actually determine the ratio of these coefficients. So the thing we're going to talk about now is how to set up the equivalent scattering question in 3 dimensions. But the actual evaluation of the scattering cross-section will come down to boundary value problems or perturbation theory, and we will tackle that afterwards. So this was the recap of how scattering worked in 1 dimension. Now let's talk about what the picture looks like in 3. Any questions? Everybody good with this recap? Okay. So for scattering in 3 dimensions, the setup is conceptually very similar. We specify an incoming wave. So we will have psi incoming, and let me give it some normalization. I think I call this A e to the I k incoming dot r. So this is a plane wave moving in some particular direction with a wave number and a direction in 3-dimensional space. And then we will want to find all possible outgoing waves. Or scattered waves. So we will find psi scattered equals something. We have to figure out what that something is. What does the scattered wave look like far away from the potential? This is a solution to the Schrodinger equation. Doesn't necessarily have to look exactly like this. And then by matching the boundary conditions, the potential, that will determine psi scattering in terms of psi initial. Psi scattered wave in terms of psi initial. And then once we have this, we can compare the probability currents. We'll talk about the probability current, which is now a vector in a specific direction, J incoming. And we will talk about the scattered probability current, J scattered. And we will talk about the amount of probability or the probability flux in a particular direction. That is what will define the transition rate and eventually the transition cross-section. Probability flowed into an area. So these are sort of the steps, and it's very similar to what we did in 1 dimension, except for the increase in number of directions things can go. The picture looks something like this. You have an incoming particle with definite momentum, h bar k initial. So let me call this p incoming. So this thing is coming in as a plane wave. So its wave fronts look like this. It's coming up and it's going to interact with some potential. Comes in from minus infinity. And you're going to interact with the target. So let me draw it kind of like a bullseye. So you have a potential V of R over here. After this wave hits that potential, it gets scattered off, and it has contributions that go in different directions. So the outgoing wave will look something like this. There may be some angular dependence to it, but this outgoing wave we will write in terms of a spherical wave. So this was my psi incoming plane wave. This will be my psi scattered spherical wave. And the question is, if I solve this by boundary conditions, so say I am able to figure out what psi scattered is given psi initial, then how much of this probability is going in a particular direction? So we will pick out a particular angle, solid angle d omega, which corresponds to a particular area element dA at a given distance r. And we will ask how much of this probability, J scattered, is flowing in that particular direction. This is what will define the scattering question. We will leave off for the moment the question of how do I figure out psi scattered given psi initial. Much like in this case, the particular values of these coefficients require you to solve the boundary value problem. But you will define the observable, like the reflection and transmission coefficients, in terms of those ratios. So this is how you pose the problem. So the first thing that I want to focus on is what is the form of that outgoing wave solution? I pointed it out here as a spherical wave. Let's discuss how that works. All right, so the idea is that we are solving the Schrodinger equation as r goes to infinity, very far away from this potential. In close to the potential, the wave function is doing something very complicated. But we have to assume that my boundary condition at r goes to infinity is so far away that it's free from the influence of the potential. So we are solving it for a free particle in 3 dimensions. R from the target, we have to assume that the potential V goes to 0. So if that is the case, then asymptotically far away, on the other side of the universe from the target, these guys behave like free particles. Asymptotically r going to infinity, we have free particle solutions. So the starting point is to write down what is the time-independent Schrodinger equation in 3 dimensions for a free particle. We have minus h bar squared over 2m d squared dr squared plus the centrifugal barrier h bar squared L plus 1 over 2m r squared. If there was a potential, it would be here, but I've taken the potential to be 0. I have the radial probability amplitude, UL of r, and this is equal to E UL of r. We have the eigenvalue equation for the radial probability amplitude. And in terms of this UL of r, this specifies the wave function solution in 3 dimensions. So the wave function psi of r, theta, and phi was the radial wave function, which is UL of r divided by r. This is that very important factor of r in converting from the sort of radial dependence to the probability amplitude, or the radial probability density when you square it. Times the spherical harmonic, YLM, theta, and phi. So this is my effective one-dimensional radial equation, just like when we did the hydrogen atom. And then this is the relation of that radial equation to the full solution. So it has some angular structure given by the spherical harmonics. And we're going to describe the radial behavior and show that that radial behavior is a spherical wave. Okay, so first we want to examine solutions to this. If I want to study the behavior in the limit r going to infinity, then it's clear that the centrifugal barrier is not relevant when r goes to infinity. Just like any decreasing potential, if r goes to infinity, this denominator goes to infinity and the contribution of the centrifugal barrier goes to 0. So let's drop this, set it equal to 0 for r going to infinity asymptotics. So the equation that we would like to solve asymptotically is minus h bar squared over 2m d squared UL of r dr squared equals the energy, which let's write it as h bar squared k squared over 2m UL of r. So this is the energy E. So now I can cancel most of these dimensional coefficients. And I get a very simple differential equation, d squared UL dr squared equals minus k squared UL, which is a differential equation everybody knows how to solve. The solutions are plane waves, incoming plane waves and outgoing plane waves. So there are two solutions. We have UL of R equals A e to the I kr plus, let me call it A prime, e to the minus I kr. This one clearly corresponds to an outgoing wave. This one clearly corresponds to an incoming wave. So for specifying the initial conditions, we have an incoming wave, which is the plane wave, this e to the I k dot r. For the scattering wave, we're looking for a solution of this form, and I'm going to choose it to be the outgoing wave solution. This is my freedom to define what kind of problem I'm asking. I'm not asking about an incoming spherical wave, I'm asking about an outgoing spherical wave. So let's choose the solution of this form. So now I can go back and plug it in here. Since I've got it right in front of me, why don't I write it underneath? If my radial wave function is e to the I kr, then my overall wave function together, including all of the radial behavior with that 1 over r and the spherical harmonics, is psi scattered of r, that is e to the I kr over r. I have spherical harmonics, YLM, of theta and phi. This is one possible solution for one definite value of L and one definite value of M. In general, I can have a sum of all of them. So let me write it as a sum of all coefficients Lm, and I'll give it some coefficient BLM.
So is the A coefficient in the UL of R, is that integrated into the BLM?
Yeah, I think for consistency, I should be calling these things B because now I'm going to match it onto the A that I was calling it over there. So maybe let me call this B and B prime. This B would be the solution for a particular L and M. And now I'm going to sum over many possible ones that could have different coefficients, so I call it BLM. So far, so good?
Thank you. Yes.
Okay. Okay, so now we found the form of the outgoing wave. All right, so altogether, as r goes to infinity, my total wave function includes both combinations. So psi of r asymptotically, as r goes to infinity, contains two pieces. It has psi incoming of r plus psi scattered of r. These are the free particle limits. The incoming wave has the form a e to the I k incoming dot r. The scattered wave has some coefficients. I have e to the I kr over r, sum over all L and M, coefficients B, L, M, spherical harmonics, Y, L, M of theta and phi. And I want to define something comparable, right? I want to define the ratio of outgoing to incoming. That was what was relevant in one-dimensional scattering. We had B over A or C over A, those ratios of coefficients that determine the overall reflection and transmission probabilities. So let me factor out this coefficient A in front and talk about just the ratio of the two terms. The I k incoming dot r plus the I kr over r, and it just rescales the coefficients. Sum over L and M, BLM divided by A. YLM of theta and phi. So this is the pure incoming plane wave. This is the pure outgoing spherical wave. This thing is all of the angular dependence. So let's just give this thing a name. This is what is referred to as the scattering amplitude. This is a definition F of theta and phi. It could be any complicated angle dependence you want, but this is the angular structure that pre-multiplies the outgoing plane wave, the outgoing spherical wave. And this is defined as the ratio of the plane wave coming in to the spherical wave going out.
So that's what we integrate over the solid angle to find the probability? Okay.
So what we'll work out next is what is the relationship of this F to the probability current, and then to the transition rate, and then to the cross-section. And yes, this is the object that ultimately becomes the building block of the cross-section and everything else. So this is your analog of the transmission coefficient or the reflection coefficient. Really, it's more like the square root of those things. But this is the building block for scattering in 3 dimensions, the same way R and T were the building block for scattering in 1 dimension. So ultimately, what matters here is that I have a definition, that I have a plane wave incoming dot R plus e to the I k r over R spherical outgoing wave times some angular dependence, F of theta and phi. This includes both the information about how the spherical wave is distributed in angle, and it tells you what is the magnitude of the spherical wave. How big is the scattering probability compared to the incoming probability current?
And just one more clarification. K incoming is not the same as K in the second term, correct?
The magnitude is the same, but the direction is different.
Right, okay.
I'll put that out explicitly here. So to summarize, so the energy of the free particle is h bar squared k squared over 2m. The k incoming, you might say, is that magnitude k associated with the energy times a unit vector for the incoming wave. Let me call it, let's say, n incoming. The k scattered, or k outgoing, or k final, whatever we're going to call it, has the same magnitude k because it corresponds to the same energy. This is infinitely far away from the potential where 100% of the energy is kinetic. And this is just going in some different direction. So this is in the radial direction ER. And phi. So this is incoming plane wave with magnitude k, energy E in a direction that I choose. The outgoing state has the same magnitude, the same kinetic energy, but it goes in any possible direction. So I want to look at the answer, the probability current, as a function of theta and phi for any given direction of the outgoing wave. But yes, to answer your question, how are they related? They are related because they have the same magnitude, corresponding to the same energy.
I mean, I guess I don't want to get too far ahead. Is it not more efficient to? I mean, this is the general case right now. But would we not eventually look at k incoming in the rest frame? Would we not just assume k incoming is in the same direction as whatever we choose our R to be? Because you say
you're asking about if this is general enough?
No, the one above it, n incoming. Because right now we have it as k dot R. Wouldn't we always choose R to be in the same direction as n incoming?
No. So let's see. So what I have in mind is sort of you have your incoming wave like this, your target looks like this, and you're asking about what is the probability current in a particular direction defined by R. So if R is from the scattering potential at the origin in a particular direction that you are going to observe it.
Oh, okay. I was confused as to what.
Okay, yeah, sorry if that wasn't clear. So you have an incoming wave which is in a particular direction we define. That is usually chosen to be the z-axis. And then one will describe the direction of the scattering relative to that. So if this is, let's say, the positive z-axis by definition, then the magnitude of that angle is the polar angle theta. And then one can also define it as a azimuthal angle phi, which would tell you how far out of the board or how far into the board it goes relative to some arbitrarily chosen x-axis.
Right. Okay. Thank you.
Okay, sure. Okay, so how is this related to observables? We have to express the probability currents. Now those calculations are similar to what we did before, but they're a little bit more complicated because of this three-dimensional form. All right, so what are the probability currents? So J incoming is now a vector that is minus I h bar over 2m psi incoming psi incoming star grad psi incoming, and let me just write minus complex conjugate. So if I plug in the form of my psi incoming with psi incoming is A e to the I k incoming dot r. This is the contribution of the incoming plane wave in a particular direction that you are asking the question about R. Let's see, so then my gradient of psi incoming is A, the gradient here brings down I k incoming, and I still have e to the I k incoming dot R. So when I plug this back in, I take the complex conjugate of this thing, and I multiply it by this. So J incoming vector is minus IH bar over 2m. This first factor is psi star, A star e to the minus I k incoming dot R, times this gradient, A I k incoming e to the plus I k incoming dot R, minus the complex conjugate. And so just like in the one-dimensional case, I get the magnitude A squared telling me how much probability is coming in. This plane wave cancels that plane wave, and I'm just left with the IK. And then when I subtract the complex conjugate, I get a factor of 2. So the incoming probability current from the plane wave that we started off with is minus IH bar over 2m. From the calculation, we got absolute value of A squared times 2I k incoming. And again, it's no accident that the 2I cancels the minus I and the 2, and I get the 3D version of what we had in one dimension. I get the total probability, which is coming in, A squared, times the velocity, h bar k incoming, divided by the mass. Probability times velocity. That is my probability curve. Now we do the same thing for the scattered wave. So this is minus IH bar over 2m, psi scattered conjugate, grad psi scattered, minus its complex conjugate. With psi scattered is, we define it to have, let's say, A times the scattering amplitude, f of theta and phi. F was the ratio of that magnitude to the incoming wave A, times e to the I k r over r. Yes. Okay, so now we need to take the gradient of this thing. Since this is expressed in spherical coordinates, let's write the gradient itself in spherical coordinates. The gradient operator is in the radial direction ddr, plus in the polar direction, I have 1 over r dd theta, plus in the azimuthal direction, I have 1 over r sine theta dd phi. Now, one thing I immediately know about this, since I'm interested in the r going to infinity asymptotics, if I'm far enough away from the target, the direction of the plane wave must be purely radial. So as r goes to infinity, this thing gets small, this thing also gets small. So I can freely ignore all of the directional information of the wave except the radial part. So far from the target, the wave is purely radial. This is equivalent to what every undergrad knows, that beams of light coming from the sun are parallel. They are coming from a source that is so far away, it is infinitely far away, that all of that difference in the direction can be totally ignored. Okay, so keeping only the radial part of the derivative, I have grad psi scattered is, let's say, radial unit vector dvr, and then psi scattered is a times f e to the I k r over r. Now I get two terms. Something in the radial direction, let me pull out the coefficients a, f, radial unit vector. If I differentiate the exponential, I get I k e to the I k r over r. If I differentiate the denominator, I get minus e to the I k r over r squared. Obviously, this is the term that I want. This is the one that has the same form as the plane waves as before. This one is imaginary. This one is real. After I get rid of that phase factor up here. This one is going to end up canceling out. This one is going to be the one that gives me my probability curve. So what do I have? J scattered is minus IH bar over 2m. Let me pull out the a squared f squared, because that's always going to be the same. So I have psi star, which is going to be e to the minus I k r over r, grad psi, times radial unit vector I k e to the I k r over r minus e to the I k r over r squared. Minus the complex conjugate of this thing. Minus e to the plus I k r over r, radial unit vector, minus I k e to the minus I k r over r, minus e to the minus I k r over r squared. So, as promised, e to the minus I k r perfectly cancels those phase factors. E to the plus I k r perfectly cancels those phase factors. I have I k minus negative I k. That's going to double it and give me a factor of 2, just like before. I have minus 1 over r squared minus positive 1 over r squared. Those are going to cancel completely. It is only the imaginary part of this thing that survives. So what I end up with is J scattered equals minus IH bar over 2m a squared f squared. Everything is in the purely radial direction, ER. And what I have left from the calculation is 2ik over r. Oh, squared, because there's 2 of them. This one over r and that one over r. That's why it looks funny to me. All right, just like before, the 2i cancels the minus I and the 1/2, and I get total outgoing probability, a squared f squared, h bar k over m with a 1 over r squared in the radial direction. Yes. All right, so this is my outgoing wave. Again, you can identify the total probability going out, the velocity of the outgoing wave. Here, the direction means that this outgoing probability is being spread out. It's being thinned out in 3 dimensions. I have a total amount of probability spread over a sphere of surface area 4 pi r squared. So the probability gets diluted as a function of r with 1 over r squared from that volume of the surface area of a sphere. All right, let me copy over the incoming probability current that we had before. That's J scattered incoming probability current was A squared H bar K incoming over M. Now we're in a position to address the observables. How much probability is going in a specific direction? All right, so the idea is to say that the scattered currents, A scattered moves probability into an area dA, and let me write this as a vector area with the unit normal to that area, at a rate dr given by. So before I write down the formula, let me again remind you the picture. We have P incoming, H bar K incoming. That's my incoming plane wave. I scatter off the target some potential D of R. And now I'm asking outgoing plane wave or outgoing spherical wave. So I scatter of R. And I'm asking how much of that wave is going in a specific direction. So if I pick out an area dA far away from it at a distance R, that corresponds to an angle d omega, solid angle d omega. Where remember, d omega is sine theta, d theta, d phi. That's the angular part of the volume element in 3 dimensions. All right, so that rate at which the scattered current is delivering probability into the observed area dA is just J scattered dot dA. And that area dA is, if this is length R, then that dA is R squared d omega. And if I make this thing a vector, then that vector is pointing in the radial unit vector direction. So this is going straight on into a tiny section of a sphere, sort of head-on collision, no angle, and the flux is just J dot dA. So this is J scattered dot R squared d omega radial unit vector. And now I plug in J scattered, and I get A squared scattering amplitude squared H bar K over M, 1 over R squared, which multiplies exactly R squared d omega. So you have exactly a compensating effect. The probability going out gets diluted by the area of the surface area of the sphere. The amount of surface area contained within a given angle increases at the same rate. So this 1 over R squared cancels the R squared. And what I get is the differential rate of probability flow per unit solid angle is A squared F squared H bar K over M. This is good. This is close to a final answer, but it depends on how much incoming current we have. The better quantity is one that is independent or normalized by the incoming current. That is the cross section. The cross section is independent of the incoming beam flux. D sigma d omega is 1 over the magnitude of the incoming probability current times the rate. So it is the rate per unit beam. So I get d sigma d omega. The cross section is 1 over the incoming probability current, which was A squared H bar K over M. Same K incoming as outgoing, just like Nick asked about conservation of energy. Times the differential rate, which is A squared F squared H bar K over M. And you see just by magic, a squared and the velocity cancel. Outgoing velocity is the same as incoming velocity. The outgoing probability is proportional to the incoming probability. And what is left is the sigma d omega is the scattering amplitude f of theta and phi squared. So this is comparable to what we had in one dimension, where we had reflection coefficient was b over a squared. Transmission coefficient was c over a squared a prime over k. This is now the version in 3 dimensions where you can go in lots of different directions. It looks more like the reflection coefficient formula because in this setup, the potential never went to 0. Right? The potential was 0 on the left-hand side and it was just a constant to infinity on the right-hand side. That's why this factor isn't 1. In the current setup, the potential is non-zero only in some region. And if I go infinitely far away anywhere, I always go out with the same velocity I came in. So that's why you get just a pure ratio of coefficients, which is what the scattering amplitude is. Okay, so the purpose of this exercise was to make contact between one-dimensional scattering that you guys had lots of practice with last semester and how that idea gets carried over into 3 dimensions. The basic building block is that ratio of outgoing wave to incoming wave, which is called the scattering amplitude. That quantity absolute value squared gives you the observable, which is the scattering cross-section. So if this is what the physics coming in relates to the observable is, the next question is how do I figure out what the scattering amplitude is? This is equivalent to saying in one dimension you had to solve the boundary value problem to figure out what those coefficients are. If you are able to solve the boundary value problem exactly for the potential, then that will immediately give you exactly what the scattering amplitude is. Usually that's very hard. And so instead we will solve it order by order in perturbation. So far we have established the definition of the scattering amplitude. F, that came in from saying that the total wave function asymptotically as r goes to infinity is equal to psi incoming plus psi scattered, and this is something of the form A e to the I k incoming dot r plus e to the I k r over r times f of theta and phi. So the basic building block is the scattering amplitude and the relation to the observable, which is the cross-section. Sigma d omega is absolute value of f squared. So then how to calculate f? Your 2 choices are solve the boundary value problem exactly. Or to do it order by order in perturbation. Okay, one other point before I move on to the repeat from last class about calculating things at first order in perturbation theory. That is the relation to the momentum transfer. We call that h bar q. So the idea was if I had an incoming wave with momentum p initial is h bar k incoming. I hit the target somewhere and I go off in a different direction. Now I have P final, which is H bar K, let's say outgoing, which is magnitude H bar K in some radial direction defined by theta and phi. H bar Q is the difference between these, the momentum transfer to the target. Momentum delivered or not delivered to the target, the momentum absorbed from the target. So H bar q is defined to be the difference between your final momentum and your initial momentum. This magnitude of the momentum transfer q is related to the scattering angle, right? If I come in and I absorb just a little bit of momentum from the target, I'm not going to get deflected very much. My angle theta would be very small. If I come in and I absorb a huge amount of momentum from the target, my angle theta will be very large. So there's a relationship between this magnitude of the momentum transfer and the scattering angle theta. That comes from squaring this thing, right? So h bar squared q squared is p final minus p initial squared. That's p final squared minus 2 p final dot p initial plus p initial squared. But energy is conserved, so p initial squared and p final squared are the same thing. Pi squared equals pf squared, and both of them are equal to 2 times the mass times the energy. So h bar squared q squared, if I set all three magnitudes to be the same thing, this is my p initial squared, and I have 2 minus 2 cosine theta. Where that theta is this theta. If this was the z-axis, then this theta is the spherical coordinate theta, the polar angle with respect to the z-axis. So this is 2 p initial squared, 1 minus cosine theta. And if I want, I can use the double angle formulas and write this as 2 sine squared theta over 2. And if I want, I can even convert from the initial momentum to the energy. So this is 8 mass energy sine squared theta over 2. Whichever version of these formulas is most intuitive is fine. The important thing is that this momentum transfer involves a mix of 2 ingredients: how much energy you came in with and what your deflection angle is. So if I came in with 1 billion electron volts worth of energy, even a tiny deviation, a small amount of angle, would be a big amount of energy transfer. So it's proportional to the energy or proportional to p squared. It's also an increasing function of theta. So it is often useful in cross sections to talk about, instead of, let's say, d sigma d omega, often useful to write it is d sigma dq squared, because you can convert from q squared to theta.
Does this assume that it has phi independence? Because doesn't omega depend on phi as well?
Yeah, that's right. So the q is also, so the magnitude of q is related only to theta. The direction of q, the angle of q, is also related to phi. So you can talk about it, maybe let me say more generally, you can convert from this to d sigma d3q. And you can convert from d3q to d sigma times the magnitude dq squared, and then an angle d phi.
Oh, so okay, that makes sense.
Direction of q. So yes, if you have a spherically symmetric potential, for example, if it has, not even spherically symmetric, it is rotationally symmetric about the z-axis, then it will not have any phi dependence. In that case, it is a function only of q squared and not of the angle phi. So you just integrate that out and get a factor of 2 pi.
Okay, that makes sense.
Okay. All right, so now's my second chance to repeat the derivation that I did last time when I botched the factors of 2 pi because I forgot how to square things. How to calculate f. There are various ways to do it. The simplest thing that we're already equipped to do is to do it at first order in perturbation theory using Fermi's golden rule. So one method that we will use now is Fermi's golden rule. Which is valid only at first order in perturbation theory. And recall that first order in perturbation theory is synonymous with the Born approximation. Born approximation is the term that's typically used in a scattering context, but it means exactly the same thing as first order perturbation theory in the potential. So we already know how to use Fermi's golden rule. That is, the differential rate per unit final state momentum is 2 pi over h bar, matrix element of the transition amplitude. So this is P final potential P initial squared times energy conserving delta function. E final minus E initial. Calculation of all of these ingredients is straightforward. Let me see if I can do it without dropping factors this time. So first thing, energy conserving delta function, E final minus initial. If this is all kinetic energy, this is delta of P final squared over 2m minus P initial squared over 2m. When I use the properties of delta functions, this is m over P final, delta function of P final minus P initial. Magnitude of outgoing momentum is the same as the magnitude of the incoming momentum, and there's a conversion factor between the energy and the value of the momentum. Second thing is evaluation of the matrix elements. P final, potential, P initial. I evaluate this thing in coordinate space. This is integral D3R. I have the incoming wave function complex conjugate, which is 1 over 2 pi h bar to the 3 halves, e to the minus I over h bar, P final dot R, times the potential V of R, times the outgoing plane wave, 1 over 2 pi h bar to the 3 halves, e to the plus I over h bar, P initial dot R. So altogether, I have 1 over 2 pi h bar cubed, integral D3R, V of R, e to the minus I over h bar, P final minus P initial dot R. P final minus P initial we write as h bar cubed. So this object is just the Fourier transform into that momentum cube. E to the minus I q dot R V of R, which I might write compactly as the Fourier transform E twiddle of Q. So this part went fine last time. The thing that I botched was when I squared this, I didn't square this factor. That's why my 2 pi h bars didn't work out. All right, so let's plug it back into the rates. dr d3 P final, I have 2 pi over h bar up front. From the matrix element squared, I have 2 of these things. So I have 1 over 2 pi h bar cubed V twiddle of Q absolute value squared times m over P final delta of P final minus P initial. So altogether, this is 2 pi over h bar, 1 over 2 pi h bar to the 6th, V twiddle of Q absolute value squared, m over Pf, delta P final minus P initial. Now I want to convert from this rate per unit final state momentum whose magnitude is fixed by the delta function, but whose angle is free. So let's write that volume element, d3 Pf, in spherical coordinates, is Pf squared dPf d omega, where again, d omega is sine theta, d theta, d phi. So I'm going to integrate out the magnitude of Pf and use the delta function to fix it. Rate per unit solid angle is defined as, let's say, integral dP final d rate dP final d omega. And that d rate dP final d omega is a factor of Pf squared from the rate per unit d3 Pf. So this is dPF, P final squared, dr d3pf. So I multiply this thing by pf squared, that cancels the 1 over pf and puts another one upstairs, and I integrate over the delta function. So I get 2 pi over h bar, 1 over 2 pi h bar to the 6, b twiddle of q squared, and now I have m p final, and I've integrated out the delta function. All right, the last step, to go from the rate to the cross section. D sigma d omega is 1 over the magnitude of the incoming current. D rate d omega. The incoming current is a plane wave. Its magnitude is 1 over 2 pi h bar cubed. And its velocity is p initial divided by the mass. Right, so the overall normalization of this plane wave, right? Each one had 1 over 2 pi h bar to the 3 halves. The current is a wave function squared, so it's got 1 over 2 pi h bar cubed. The velocity is p initial over m times everything else. 2 pi over h bar, 1 over 2 pi h bar 6, b twiddle of q squared, m times p final times delta function. No more delta function, we integrated it. All right, so here's where my factors got botched last time. These guys should not cancel 100%. This one cancels 3 of them. The P initial is the same as P final, so this cancels that one, and I get 2 factors of the mass upstairs. D sigma d omega is 2 pi over h bar, 1 over 2 pi h bar cubed. Now I have m squared from all of these various conversion factors, times v twiddle of q, absolute value is squared. So finally, I pull all of this stuff inside. The overall number here, right? So I have 1 over h bar to the 4th. I have 2 pi upstairs, 2 pi cubed downstairs. So I have 2 pi squared downstairs. And I have n squared upstairs. I'm going to pull this inside the absolute value squared. So this is absolute value squared, 2 pi h bar squared m v twiddle of q squared. And if I plug back in what this thing is in terms of the Fourier transform, it is minus I q dot r v of r. So this is my evaluation of the scattering cross-section using Fermi's golden rule, which is to first order in perturbation theory. What I know from scattering theory in general is that d sigma d omega should be equal to the absolute value of the scattering amplitude squared. So this thing inside the absolute value should be the scattering amplitude. So what we find out is to first order, or Born approximation, scattering amplitude f of beta and phi is negative m over 2 pi h bar squared, Fourier transform of the potential. It might also be useful to think of this as f of q vector, since the magnitude and the direction of q tell you precisely about the direction of theta and phi. So when you evaluate this thing, the right-hand side is obviously a function of q. That's where the angle dependence comes in. All right, we're out of time. Otherwise, I would work through an example. Let me just say one last thing. In going from this absolute value squared to the f, I have, out of nowhere, introduced a minus sign. Obviously, that doesn't do anything when I take the absolute value squared. That's just a convention. But when we actually calculate this thing using order-by-order perturbation theory, we will get that minus sign directly. I don't actually know that it matters for anything, since the observable is always squared, but it does naturally come with that sign. Okay, so here once again is the derivation without botching factors of 2 pi h bar, hopefully. The point is now you can solve scattering problems for a given potential, just like on the homework. I have an example of the Yukawa potential that we will work out on Wednesday. Given the potential, Fourier transform it, multiply it by some constants, and square it. You're done. The only difficult part is performing the Fourier transform for a given potential. So you will do that on homework for the Gaussian, where you've already done that Fourier transform, and you will do it for the 1 over r squared potential, which requires a little bit of regulating the infinities where r goes to 0. Any questions?
So finally, the calculating for the cross section will give us a function of theta and phi.
Yes, and that's equivalent to saying it's a function of q, the vector q. Typically, if your potential is spherically symmetric, it will depend only on the magnitude of q, which means it depends only on the polar angle theta. So if E of r equals V of the magnitude r spherically symmetric, which is the case of basically everything that you calculate, then your scattering amplitude will depend only on the polar angle theta, which means it's a function only of the magnitude q squared. So typically, this is what you will find when you do that three-dimensional Fourier transform, that it depends only on the magnitude of q.
And that r goes to infinity, this dependence will disappear or what?
Which dependence will disappear?
After the scattering, if r goes to infinity.
So this is the solution as r goes to infinity. As r goes to infinity, you get exactly a plane wave or a spherical wave. And this describes the magnitude of the spherical wave in a given direction. So this is already using the solution when r goes to infinity.
Oh, okay.
Okay? All right, thank you guys very much. We will carry on with this on Wednesday.
I had a question, Professor.
Yes, sir. I apologize for not getting back to you now. Did you still have
that's okay. Would you be available in your office hours today after the lecture or tomorrow morning?
I will definitely be available during regularly scheduled office hours this week. I can meet later today if you need to. I think I may have another meeting right after this, but we can set up a time today if you still have questions.
So the regular office hours are tomorrow morning, right? From 9 to 10?
No, the regular office hours are on Thursday.
Oh, they're on Thursday.
Morning from
Okay.
9 to 11.
Would you be available today in the afternoon sometime?
I think so, yeah. Let me double check my calendar and I'll send you an email.
Okay, yeah, that works.
Okay, thank you. Again, sorry for not getting back to you this week.
That's okay, that's okay. Thank you, Professor.
No problem.
Thank you.
My apologies to you as well, Masood. Did I answer your questions at the beginning of class about
Yes.
when the exam's coming up and when things might be cut off?
Yes, I got the answer. Thank you, Dr. Sibu.
Sure.